And right, it's recording. Hopefully it's recording to the cloud, so we'll see. All right. So last time we talked about different levels of description, and we talked about coarse graining. We talked about the idea of different levels of description and the idea that you can start off with a microscopic Hamiltonian, coarse grain all the way to the system scale and get thermodynamics, or you can stop halfway through and get a coarse-grained, mesoscopic, smoothly varying description of a physical system. And that's going to be an important part of the way we approach our topic. We introduced the notion of a functional integral, which I haven't yet told you how to compute it, just the basic idea that you sum over all the degrees of freedom, just as you do in a statistical mechanical trace. We talked about phase transitions being regions where the partition function is something that is non-analytic, and therefore it requires an asymptotic limit to be taken, and that asymptotic limit could either be n goes to infinity limit if you're talking about a spin system, or it could be n goes to infinity, the volume going to infinity, and then the ratio of the number of particles per unit volume being a fixed number, the particle density in the case of, say, a particle system like a fluid. We talked about the properties of the Ising model, and I showed you that the Ising model at low temperatures will basically, the spins will like to line up, and if you have an external magnetic field pointing slightly up, the spins will point in the up direction. If you have a magnetic field that is pointing down, the spins will point in the down direction. If you're much less than the critical temperature and you take the external magnetic field away, the spins will still stay pointing down, or in the first case, pointing up. And so the magnetization will have a discontinuity. We talked about the way that you can calculate in statistical mechanics by taking derivatives. And I showed you that the magnetization is a derivative of the free energy with respect to the external magnetic field. That's shown over here on the left. So we did talk about the classification of phase transitions. We talked that the free energy per unit volume is always a continuous function. A derivative of it can be discontinuous. If it's the first derivative, it's a first order phase transition. If it is a higher derivative that is discontinuous, then classically you would say whatever nth derivative it is, that's an nth order phase transition. Today we know that you get other non-analyticities other than discontinuities. You get divergences. And so today we talk about discontinuous phase transitions being first order transitions and continuous transitions being anything other than that. Then I want to tell you, I showed you how to differentiate the trace and derive the free energy per unit volume. And what I want to do today is I want to talk about spontaneous symmetry breaking. I'm going to show you, you've all heard that phrase. I want to show you what it actually means. We're going to talk about an associated concept which you may not have heard about called ergodicity breaking. And I'm going to show you that that's an essential part of phase transitions. And in fact, without that, we won't be able to even have a phase transition. And then we will, in this lecture, we will show another version of the impossibility of phase transitions. And then if we get time at the end, we'll talk about the simple version of mean field theory. So we're going to do a lot of different things today. So let me now get started. So last lecture, we had talked about how you can derive the magnetization by differentiating the Hamiltonian with respect to the external magnetic field H. So I want to now begin by considering the case where the external magnetic field is spatially varying. So why on earth would I want to do that? So why? And the answer is the following. Come on in. Yep. The answer is this. If H is equal to a constant, then I can get thermodynamic variables, e.g. the magnetization M. But if H is actually a function of space, so it depends on what lattice site the magnetic field is supposed to apply. So if I have H is equal to HI, then we'll later see that from that we can get correlations in space. And so everything we do in statistical mechanics, we get by doing a differential, either with respect to a uniform field or with respect to a spatially varying one. So let's suppose I make the external magnetic field be, in principle, a different number on every different lattice site. Then what does my Hamiltonian become? Well, then my Hamiltonian looks like this, minus some I equals 1 to n, hi, si, each spin interacts with the external magnetic field that is at its particular lattice site. And then I have the exchange interaction, the si sj term. That's the term that gives us all the difficulties, because this is the term that makes statistical mechanics a many-body problem. And then this is an exercise for you to do after class. So it's not a formal homework exercise, but I want you to check this. You should check that if I compute the derivative of the free energy with respect to the external magnetic field at a given site I, that is going to be a quantity that depends on what I is. Okay, so you tell me what I is, 17. I differentiate the free energy with respect to the magnetic field at site 17. And when I do that, then I will get the expectation value of the spin at the site I. So, and that's going to be true for any I. So that's what I want you to check. And that will check your understanding of differentiating statistical mechanics. All right, so now let's talk about the impossibility of phase transitions. So So what I want to do now is I want to do it in a different way than we did before. Before, what we argued was if you have a phase transition, you have to have a non-analyticity. If there's nothing analytic, if everything is analytic, then you can't have a phase transition. So that's certainly true. Now I want to show you that symmetry also plays a role in understanding phase transitions. So now I'm going to show you that from symmetry alone, we can show you that phase transitions are not possible. So let's have a look at that. So here is our goal in this section, is to see that there's a possibility is a consequence of symmetry. And so I'm going to show you that by looking at the symmetries of the Hamiltonian and showing you how they're reflected in the symmetries of the thermodynamics. So that's our goal, and our strategy is use the symmetries of the microscopic Hamiltonian to determine the symmetries of the thermodynamics. Okay, so let's get started. So here is our Hamiltonian. H is equal to minus H sum over I Si minus J sum over nearest neighbors Si Sj. So notice that what happens if I now do a spin flip. So let's suppose I look at this transformation. I take every spin, and I write these curly brackets, I mean the set of all spins, and now let's suppose I make that go to minus Si. So that means I take every single spin in the system, take a snapshot of the configuration, reverse every spin. And I can do that for every configuration. I can do it for every configuration average of all those configurations. So let's have a look at what happens here. So this we can think of as being a spin flip. You might say, well, this is like going backwards in time. I've got to spin up. Now, before that, it was down. So if I now make it down, then it's kind of like a time reversal. There's no real time in equilibrium statistical mechanics, but people use that term in any case. Let's suppose I do that, and I also flip the sign of the external magnetic field. So H goes to minus H. So those are two symmetry transformations that I can look at. And then what happens when I do those symmetry transformations is that my Hamiltonian, now expressed as in terms of minus Si and minus H, well, you can see what's going to happen. This is going to be the same as the Hamiltonian. If I change the sign of S, then this term, the first term over here, that's going to change to minus, but the external field H has also changed to minus, so those two minuses make a plus. And if I change the sign of both spins over here, then Si goes to minus, Sj goes to minus, two minuses make a plus. So in fact, once I've done that, once I've made these two transformations, I still get the same value that I got before. So that is a symmetry of the Hamiltonian, and in particular, we're going to be especially interested in what happens when the external field is equal to zero. And the reason we're interested in that is because that's where we have a phase transition. Allegedly. All right. I've got an upside down. I've got an upside down triangle of dots, and that is not an emoji. That means because. Okay, was there a question?
Yeah. That third line bottom are especially what indicates H is
Interested. Okay. All right. So now we're going to look at the consequences of this symmetry. And so for those consequences, by the way, I do encourage you to take notes because you'll learn more if you take your own notes, but I will post my notes also on Teams as well. So you actually have my notes, and you also have the book, the printed notes. So you have handwritten notes, printed notes, videos, whatever different way you like to learn, you should have everything you need. All right, so now we're going to look at the consequences of this. And so what we're going to do is now we're going to plug these symmetries into the partition function. So let me show you how we will do that. So I take this let me label this equation with a little star. So what I'm going to do is I'm going to compute, for example, what is z of minus h and j and t. So what do? Well, the partition function is just the sum over all the spins of e to the minus beta times the Hamiltonian. And now I've asked you to have on the left-hand side minus h. So I'm supposed to put minus h in here. And then I have j, and then I have all my spins. Okay, so that's what we have to compute. Now, as I keep emphasizing, I'm going to keep doing it until you get sick of it. This SI here is a dummy variable. So it's just the variable of integration, if you will, or the variable of summation. That appears in here as well. So I can make a change of variable. So I can, if I want to, and I do want to, I can now make a change of variable of all the spins going to minus that spin. I'm allowed to do that because we're just summing over all the spins anyway. So if I'm doing an integral over x from minus infinity to plus infinity, and I say I'm going to define y to be minus x, then my integral goes from minus infinity to plus infinity, but now it goes from y. So I'm just making a change of variable. So if I change all the spins to minus, but I'm still summing over all the spins, in that sum of 2 to the n terms, I will still get to every possible spin configuration that I would have originally. So then I can simply say that this then is equal to the sum over minus SI is plus or minus 1, e to the minus beta h of minus h, j, and minus SI. Okay, so all I've done is make a change of variables. And now because of star, this equation over here, the Hamiltonian of minus SI and minus H is the same as the original Hamiltonian. So this thing then is the same as the partition function of H and J and T. Okay, so the partition function has that symmetry. Then what that means is that the free energy has it as well. So that means if I look at the bulk free energy as a function of H, J, and T, then that is equal to the bulk free energy of minus H, J, and T. So that's a symmetry of the thermodynamics, and the free energy then is an even function of the external magnetic field H, and this result was not made with any approximation. It is an exact result. Okay, so now we know that. Yes, question?
Possibility, are you talking about like just restrictions or like just things that cannot?
Well, hold that thought.
Okay.
Hold that thought for 30 seconds. Okay, because I'm going to show you that it's impossible. Okay, literally impossible. So what that means is that f of h, j, and t is equal to f of minus h, j, and t. So if I want to compute the magnetization, remember last time I showed you that the magnetization is minus 1 over n df by dh. So now I can go ahead and use that. So then n times the magnetization of h is equal to minus df by dH of H. So that's the definition. But because of the line above, that means it's equal to minus dF of minus H by dH. And that then is the same thing as dF of minus H by d of minus H. And dF of minus H by d minus H, that thing is equal to minus n times n of minus H. That's the magnetization of minus H with a minus sign, just by definition. So what I've just proved to you is that the magnetization as a function of H is equal to minus the magnetization of minus H. It's an odd function, and this is an exact result. Okay, so everybody happy with the algebra, the 3 lines of algebra on the left page, on the left panel? Okay, so since this is exact and it's true for any H, now set H equal to 0. If I set H equal to 0, then what I've got is m of 0 is equal to minus m of minus 0, or minus 0 is just 0. So I have that is equal to minus m of 0, and that therefore means that the magnetization in 0 external field is equal to 0. And this is going to be true for all temperatures T. This symbol here means for all. So that means that if the magnetization is always 0, then we can't have ferromagnetism. Did I answer your question now? Yeah. Okay. So that means there's no ferromagnetism. And you know what we basically did here, if you think about the interpretation of the algebra, what we were really doing was saying for every state of the system with a particular configuration of spins, there's another state of the system that we have to average over in the partition function where all those spins are flipped. And because of that, when I average over all the possible states, I end up with no net magnetization. So the interpretation of the mathematics for every state in thermal equilibrium there is another state exactly the same, but all spins were flipped. When we average over all the states, the magnetization cancels out. Okay, so again, this is obviously wrong, but why is it wrong? Well, we already know the answer to that because this goes back to asymptotics and non-analyticity. So we already suspect what the problem is here. So the subtlety in this proof is that we need to take n goes to infinity. So we know that is true. So what do we think will happen when we take that limit? Okay. So the question now is what might happen if we take the limit n goes to infinity. So here's our answer, and let's do this by drawing a sketch. So I'm going to draw here on my horizontal axis the external magnetic field, and here I'm going to draw the bulk free energy per spin. That's something that we use because as I take the limit n goes to infinity, FB stays finite, so it's not going to go to infinity. And we know that this has to be a symmetric function. So if I chose a value of n, which is say, 10, 100 or something like that, I will get a curve that is symmetric. I don't know, that was not very symmetric the way I drew it, but something like that. So this would be the case when n is less than infinity. And now when n equals infinity, then what can happen? It's got to be symmetrical. And one of the things that can happen is I get something like this. I haven't proved to you that it does happen, except I kind of did last lecture. So it could look like this. And so this is meant to be n equals infinity. And in this particular case here, what is happening at this point here, this is a cusp. So it's still symmetrical, but now what it has is a discontinuity in its derivative. So if you ask me, what is the behavior of the bulk free energy in the large n limit, FB of H in the large n limit is then the value at the origin minus ms, a coefficient, times the absolute value of H, and then higher orders of H, so something like that, where sigma is an exponent that is greater than 1. So if I have that, that would tell me what's happening here. It says right at the origin, the free energy has a cusp, and that cusp is, as you get closer and closer to the origin, it will have a linear part. So that linear part then is a discontinuity in that. So the only linear term that has a discontinuity is the absolute value of H. And then the curvature, as you go to larger and larger H away from zero, will grow as some power law of the external magnetic field. So if I have this behavior, then what I get then is as H tends to zero from above or below, the magnetization is minus dF, the bulk free energy over H, and that is equal to ms when H is greater than 0, and it's minus ms when H is less than 0. So this functional form is something that we might be able to derive from statistical mechanics, and if we are able to do that, then we'll have explained this shape. So that's the free energy as a function of external magnetic field, and what can happen, what can happen. So I haven't proved that it does happen. So all we can say is that this actually does happen. When t is less than tc. It does happen, but I haven't demonstrated it to you. Let's plot this in another way. Okay, so here's another way I want to plot this. So I'm going to plot over here m magnetization as a function of external magnetic field. Okay, why do I want to do that? Because this is going to teach us what we actually see in an experiment. In an experiment, we apply an external magnetic field to a system, look at the magnetization, and then we might let the external magnetic field go away and see if the system is spontaneously magnetic on its own behavior. So let's have a look at what what we would expect to have happen. So the first graph I'm going to draw is a graph where I assume that the system has a finite number of degrees of freedom. So if it has a finite number of degrees of freedom, we know m has to be an odd function. So the shape is going to go like this. At h equals 0, m has to be 0. As I apply an external magnetic field, the spins orient with respect to the external field. So there's a linear behavior near the origin, but eventually the magnetization can't get bigger than +1 or -1. So the curve has to look something like this. So this would be +1 and this would be -1. Okay, so that's what the curve would look like. And this is indeed true when n is equal to some n1, and that n1 is finite. Okay, so now let's draw another case. Now let's draw the case where n is a larger number than n1. So now the system is becoming much larger. Then the curve looks something like this. So this curve here is n equals n2, which is greater than n1 and still less than infinity. So now what's happened is the curve gets steeper and steeper. And now what may happen as I make n go to infinity, what we've asserted from the picture above is that it comes in like that and then comes out like that. So this is n equals infinity. And this curve comes in here. This is plus a magnetization, and this is minus ms. And I call it ms because ms means spontaneous magnetization. So that's what this picture has suggested for us. And this picture is a true picture. And this is true for t less than excuse me, the critical temperature. If I were to make T greater than the critical temperature, then all these curves would look like the brown one and the blue one. They'd all go through the origin. Okay, so this is what happens at T less than Tc. All right, so now let's move on. And I want to ask, what do we mean by the phrase spontaneous symmetry breaking? How many people here have heard of the phrase spontaneous symmetry breaking in a class, in a seminar, online? Pretty much everybody. Okay. Anybody want to tell me what it is?
Hearing it and knowing it.
Huh?
Hearing it and knowing it are two different.
Hearing it and knowing it are two different things. If you listen to a seminar or you watch a video on YouTube or something like this, not this video, but other people's videos, you might get the idea that here's what happens. At high temperatures, all the spins are fluctuating in some random direction. I lower the temperature of the system, and then just like that, all the spins start to point up or point down, and they've chosen a direction magically, and that's the spontaneous symmetry breaking. Okay, does that sound roughly to what you've been told? Yeah, everybody's nodding. Yeah, okay, it's completely wrong. Okay, it's nothing like that at all. Okay, so let's talk about what it really is. So the answer to the question is it's not in zero field. M suddenly, the magnetization suddenly acquires a non-zero expectation value. If you go to a class on quantum field theory, you might get that impression. How many people here are taking quantum field theory or have taken it? A few of you, okay. Well, so you will learn new things in this class. Those of you who haven't yet taken quantum field theory, it is the the language barrier between undergraduate and graduate level research is knowing quantum field theory and being able to at least understand it, even if you're not able to do it. So historically in this class, I've mostly had experimentalists and they've understood everything. And when they go to a seminar after the class and they hear a condensed matter theorist or a high energy physicist talking about functional integrals and Feynman diagrams and blah, 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 they're not intimidated. They know exactly what's going on and what and where to, what it all means and so on. So you'll all get that too. Okay, so that's what it's not. Okay, so what you would mean by that is then if I compute the expectation value of M, then you get some MS, and the system suddenly did that, and that's what I'm saying is no. So here's what we really mean. In the real world, not theorist's ideal world, what we really mean is the following. Step one, apply an external magnetic field that is non-zero. Okay, so let's call that step one. Step two, take the limit, apply a field and equilibrate. Okay, let the system go into equilibrium because we're always talking about equilibrium stat mech, at least not for the next few minutes. And then take the limit as h goes to 0. And then step 3, is there still a magnetization? And the answer to that question is, if t is greater than tc, then m is equal to 0. And if t is less than tc, after you've done that, then m is equal to plus or minus the spontaneous magnetization ms as I take that limit. So the process is you first of all apply a field, then you take the field away. And you can ask, if I take it away, you normally would say, well, you take the external field away, the system will then equilibrate and randomize and you'll get no net magnetization. But in some situations, it can happen that it stays, it remembers that it had been magnetized. And that happens when you're below the Curie temperature. And which direction you're magnetized in, that will depend on what the direction of the external field was. If the external field was originally in the up direction, the spins will be magnetized in the up direction. If the external magnetic field was originally in the minus direction, then your magnetization will be in the minus direction. So M will be plus or minus MS, depending on whether you took the limit h goes to 0 from the plus side or the minus side. So that's what we mean. That's what we mean by spontaneous symmetry breaking. Okay. Now, we know it's kind of impossible. Because it's impossible because for two reasons. One, you need to take the large system limit, which of course in the real world you only do approximately. The other is you have this symmetry. So now we want to understand why the symmetry is broken. Now, in the example I've shown you, the symmetry is broken by applying the external magnetic field. But then you take it away and it still stays broken. That's the mysterious thing about phase transitions. Okay. Okay, I can give you another example. I'm going to spend 30 seconds telling you this. Let's suppose you have a differential equation. Okay, it's just an ordinary differential equation that you all know and have done in classes. The solutions to that differential equation are deterministic, right? I have a solution, I have an initial condition, whatever. Solve the equation, I get a solution. Right? Let's suppose that now I add some random noise to that differential equation. Okay, is the solution going to be deterministic? Yes or no? How many think yes? How many think no? Okay, everybody thinks no. I've added some stochastic noise to the right-hand side of a differential equation. So it's a deterministic thing plus a stochastic thing. The solution is obviously going to be stochastic. Okay, now let's suppose I take the limit as the strength of the random noise goes to 0. Is the solution going to be deterministic or stochastic? Okay, answer the question with the brain that you had 5 minutes ago, as opposed to the brain you have now. Okay, what would you have expected with your brain from 5 minutes ago?
Determinist.
Say it again.
Determinist.
You would say it would be deterministic. I had a random noise, it became stochastic, I took the limit as the random noise goes to 0, it should stay back to deterministic. That's completely right, that's complete common sense. Okay. However, you can have a situation where you take that limit and the solution still remains stochastic. And we call that spontaneous stochasticity in the same way that we call this spontaneous magnetization. You applied something, you biased the system, you took it away, and yet the system retained a memory of that. So just like you can have spontaneous magnetization, you can have spontaneous stochasticity, which sounds absolutely astounding, but that's what I think happens in turbulence. And the reason we think that is because when we make models of turbulence, we can see this happens in these models. That was a phys letter I had about a year or so ago. We don't know whether it happens in real fluid, whether that's the real explanation. That's still a matter of ongoing research. Yes.
Any sort of example on the differential equation side?
So you're asking me, is there an example of such a thing?
Yeah.
There is. The example is the example that we looked at was what's called a shell model of the cascade of turbulence. Okay, so there's a particular set of differential equations. But there's other equations also associated with turbulence theory that do that. Yes, you question at the back.
So by removing the noise, you actually mean taking the limit that the noise goes to 0, right?
Yes.
But it's not exactly 0.
You're taking the limit and the noise can be as arbitrarily small as you like.
Does it equal to 0?
Taking the limit and setting something equal to 0 are not the same thing. Remember, we talked about that lecture 1 and lecture 2, that the question of an asymptotics and the question of the limiting value are different questions. Okay.
So are those two differential equations the same differential equation mathematically?
It's a very subtle question. I don't want to take too much time to answer it, but here's a question that I thought somebody was going to ask me. I thought somebody was going to ask me this question. In the case of statistical mechanics, you've told me that this spontaneous magnetization thing can happen when I go below TC. So it doesn't always happen. It's something that can happen, and this is the situation where it does happen. So if I take a stochastic differential, if I take a differential equation, add some stochasticity, then make the stochasticity go away again, for most equations, it is completely true that you will get deterministic solutions. But for some equations, you won't. And you might ask, what kind of equations does that not apply to? And the answer is, if the equation has a singularity in finite time. There's got to be some non-analyticity going on here. And that means there has to be some kind of singularity. Differential equations can have all sorts of subtle mathematical singularities, just like we have in statistical mechanics when we take the thermodynamic limit. Okay, that's all I have time to say about that. So if you're interested, ask me in Teams, would you please tell us what the heck you're talking about? Give us a reference, and I would be happy to do that. Okay, all right. So now let's talk about what is really going on in the case of statistical mechanics. So now the next question is, what is really going on here? And how can this paradoxical thing arise? So in order to answer this, we have to ask, what does it mean for the fundamentals of statistical mechanics? Okay, so the next thing I'm going to tell you is going to be a statement that you will find very shocking. So it means a lot. And so here's my answer. So the bottom line, I'm going to tell you the bottom line, the punchline first. The bottom line is that, let's talk about the fundamentals of statistical mechanics. On your mother's knee, you learnt about statistical mechanics, and you learnt that the distribution that applies in statistical mechanics is the Gibbs distribution or the Boltzmann distribution. Okay, so when we talk about the fundamentals of statistical mechanics, what we know is everything in statistical mechanics is basically you have a Boltzmann factor, and then you do some calculations, and then you compute whatever it is that you're supposed to compute. Okay, so I'm now going to tell you that it is not true that the distribution that applies is the Boltzmann distribution. Okay, so the bottom line is that the Boltzmann distribution is, as they say in Russian, not quite correct. That's the translation of what they say in Russian. Okay, and I'm going to explain to you that. So we're going to see that in most circumstances, it's perfectly true that the Boltzmann distribution applies and you can carry on using it and everything. But when we're trying to understand phase transitions and all of these things, the emergent properties, the Boltzmann distribution breaks down. So to understand how that happens, we're going to need to go back and rethink about the fundamentals of statistical mechanics. So that's the bottom line. So we're going to, so the next thing we're going to do is we're going to go back and ask, why does statistical mechanics work in the first place? You know, how many people remember when you did statistical mechanics, you learned it on your mother's knee, the reservoir and the the ensemble statistics, Boltzmann distribution, and so on. Okay, you all learned that, right? Okay, it's complete rubbish. Okay, there's no such thing as an ensemble. If I'm doing statistical mechanics of this thing, I haven't like got an infinite number of these things. I have just one. I just have one object. Okay, that is a fiction. Okay, so and if you take my class on statistical mechanics next quarter, the introductory graduate level class on statistical mechanics, which I think I'm teaching for the first time here, I will explain that where that comes from. So let's go back to the basic idea of ergodicity. And what I'm going to tell you about in this section is we're going to talk about a thing called ergodicity breaking. So spontaneous symmetry breaking is not so remarkable if you know about ergodicity breaking. But if we're going to talk about ergodicity breaking, we have to talk about what ergodicity actually is. So let's draw what ergodicity is. So let's go back to the beginning. So I'm going to imagine I have a statistical mechanical system with some spatial variables qi and associated momenta pi, and those things are vectors, and I goes from 1 to n particles. So I've got a bunch of particles bouncing around in a box, and these are 3 vectors. So this set of 3 vectors defines a 6n dimensional phase space. I can't draw 6n dimensions, I can barely draw 2. So I'm just going to sort of draw it like this. So here's my phase space. So I'll use gamma to mean phase space, at least for now. So there's my phase space. And then what happens, what you're supposed to say is that these variables, let's say, satisfy Hamilton's equations. Bless you. Let's suppose they satisfy Hamilton's equations. So the state of the system is a point in this phase space. Okay, so there it is at some time t. And then what happens is I let time evolve. So now this thing makes some trajectory. So I get some scribbly thing like that. And that's the trajectory of the system in its phase space. So now let's suppose that, that's just reformulating classical dynamics. So now let's suppose the question we're interested in is what happens to some variable that is a function of the q and p coordinates. Okay, and the question that we want to ask in particular is what is the variable's average value? And the question that we really want to understand, I can draw like this. So I want to compute. So how would I measure that? Well, what I would do is I would measure it over long time and divide by the time. Okay, so that's what I would do. So I would measure the expectation value of this variable f. It's a function of all the coordinates, and this is the dynamical measure of its average. So what I'm going to do is I'm going to average f as a function of all the q's and all the p's. I've written them as q and p as a vector, but remember, understand that as q is the vector of 3n, p is the vector of 3n. So I'm calling this q and p, where each of these are 3n dimensional vectors. Okay, everybody happy with that? And then if not, tell me and I'll explain it more carefully. And then I'm measuring this as a function of time. I'm going to call it dt. I'm going to average. So average is summing over all of these things, but I'm measuring this in continuous time. So I'm going to sum from some time to some time t max. And then I'm going to average over t max. And so that would be the average value. And then the claim is that at long times, the system becomes in thermal equilibrium. And if it's in thermal equilibrium, equilibrium means that all the transients have gone away. So the system has forgotten the memory of its initial condition. And so then you might say, well, okay, if I look at the phase space over here on the left, I'm claiming that now the trajectories fill this space in some particular way with some probability distribution, and I can look in this region of phase space and ask what is the density of trajectories in the phase space. So then in equilibrium, what is the density distribution of trajectories in phase space? And if I could measure that, then ergodicity means that the expected value of this variable as a time integral is equal to 1 over the partition function, the trace of this variable as a function of q and p times the Boltzmann factor as a function of q and p. So that and this we can think of as being a phase space, as being a measure in phase space. And what we've done is we've used the fact that the probability distribution for the trajectory being near a point in phase space so that probability, in other words, the probability of a state is e to the minus beta times the Hamiltonian over the partition function. So that's the Boltzmann distribution. That's what you learned on your Mother's Day. So we've replaced a time average along a trajectory by saying, if I look at these trajectories, after I've scribbled on the left-hand side long enough, those trajectories create a density of trajectories in phase space, and then I can just sample what that density is, and that will give me the equivalent value of what I would have got if I just did the integral over time. So that's the great thing about statistical mechanics, that we don't solve the mechanics at all because it's too hard to do. What we do is we wait so it's in equilibrium at very long times, and then all we have to do is look at the density of trajectories on phase space. And how you prove that, I'm not going to go into, but that's the fundamental notion of ergodicity. So this notion of ergodicity, what does ergodicity mean? Ergodicity comes from a Greek word that means wandering. So the idea is that the trajectories in phase space on the left-hand side wander all over the phase space, and we just average, we look at the density of those trajectories in phase space, and we can compute time average, a long time average from an average of those trajectories. Okay, what the ensemble is and all of that, I'm not going to go into here, but I will talk about it in my class next quarter. Okay, so now let's go back to phase transitions. And so we concluded that the magnetization was equal to 0, and that makes sense because every state is summed over, and we have the same thing that we had before. So the only way to get M is non-zero is if the Boltzmann distribution is not correct. More precisely, it does not apply for temperatures less than the critical temperature. So let me now explain that. I'm now going to draw for you the phase space of the system. So here I'm drawing phase space. Okay, so these are gamma, and I'm going to be interested in the case where H is equal to 0, because that's where what we're interested in. And I'm going to label the states here by whether or not they have positive or negative magnetization. We know that for every state, there is another state which is exactly the same, but time reversed, and therefore has negative magnetization. So I'm going to draw a line here in this phase diagram, like this. So these are the states with M positive, these are the states with M negative. And what our naive assumption would be is that, well, the system is ergodic, explores all of these states. And so this picture would imply that M is equal to 0, and that's what we would expect. So now we're going to say, well, maybe that's not what happens. So let's draw the same picture of phase space. It's divided up into positive and negative parts. If it were the case that the trajectory was not one that went over positive and negative states with equal amount of time, but if you started over here, then it goes like this. That would then have an M not equal to 0. And again, all of this is H is equal to 0. Of course, I could also have this situation where I draw my states, M greater than 0, M less than 0, but this time I started it over here because my external magnetic field was pointing down, and so it favored the states with negative magnetization. And then as I evolve the system, it wanders around and always stays there. So in this picture, I can have this or this. So this picture, the one at the top, this would apply when T is greater than TC. And then this picture would apply when T is less than TC. And you can see that there's two ways that this can happen, either the picture on the left or the picture on the right. So if that happens, and we have to prove that it does happen, but if that happens, then you would have a non-zero magnetization. Now you also know that this can only happen in the limit n goes to infinity, and that's indeed true. Now, do you remember I told you that emergence is a non-property of the system? So here is an example of that. First of all, it's non-mandatory, because the picture at the top could always happen, but my claim is that when you're below TC, you get either one or the other of those two things. There's two things that could happen. And the other thing I said about emergence was that there was a lack of uniqueness. And indeed, here we have multi-stability. You can either have one state or another state, either the state that points up or the state that points down. They're both equally likely. Which one you get depends on the history. So in this particular case over here, the system loses memory of its initial condition. But over here, the system remembers something about the initial condition. Okay, so when I have this picture over here, in each of these two cases, what? Oh man. Why? Please come back. Thanks. Okay, thanks for letting me know. All right. Okay. So the system remembers its initial conditions. So if you say, well, if you don't have the Boltzmann distribution, what would you say we have? Well, I would say we have this. So my claim is that the system is ergodic in a restricted region of phase space. So for T greater than Tc, the probability in equilibrium of observing the system with some given spin configuration is 1 over z e to the minus beta times the Hamiltonian of that spin configuration. That's true for T greater than Tc. And for T less than Tc, we either have P equilibrium SI is equal to 1 over Z plus e to the minus beta h of SI times a Heaviside function of the sum of the spins, or P equilibrium of SI is 1 over Z minus e to the minus beta h of SI, Heaviside function of minus SI. And this function, Heaviside function, just to remind you, is equal to 1 when x is greater than 0, and it's 0 otherwise. And what happens at x equals 0 is not a question that I want to answer right now. All right. So another way to say this is to think of it like this. Here's my phase space. I can have two different versions of phase space. Here's the states with m greater than 0. Here are the states with m less than 0. And what I'm telling you is that below Tc, what we have is that P is not 0 here, but P is identically 0 here, or P equals 0 here, and P is non-zero here. So that is the concept of ergodicity breaking. Okay. Now, I haven't shown you that it actually happens. I've shown you that this is the thing that, if it happens, would explain the idea of a phase transition. So now I want to end today's lecture by showing you that it's true. So now the next question you should ask is, how do we know this is true? And to answer this, we're going to have to do some non-equilibrium statistical mechanics. And it's going to be quite interesting. So let me tell you what the answer is.
How that relates to what we discussed.
Well, a Heaviside function is a function that is 0. Say in the look at the picture on the left, and in the region where P is equal to 0, and then is non-zero above that. That's all. So I'm just using that as a kind of mathematical equation that filters this. Okay. All right. So now I'm going to show you that this is true. And here's the strategy. I'm going to tell you the result, and then I'm going to have to derive the result and you're going to have to take a few things for granted because I'm not going to be able to spend time and explain every single part of this. Okay, so the strategy is this. We're going to compute how long it takes for a system initially with, let's say, m greater than 0 to go into the region where m is less than 0 for finite n. Okay, so the idea is this. Let's suppose I start off with my system over here on the left-hand side. Look at the pictures on the left over here. Okay, so let's suppose I start off there. All of these pictures are true. All of these pictures are true for n equals infinity. So now let's ask what happens if n is finite. Okay, then we know that you're always, when n is finite, you're always going to get this picture for any T, for all temperatures. Okay, and then what I'm going to work out for you is how long it takes for the system, when I started off in the positive region phase space, to go into the negative region phase space. And here's the result. So the result is a very peculiar equation. It says that the time that I want scales like some microscopic time scale, then e to some number times n to the power d minus 1 over d. So tau naught is some microscopic time. C is a constant of order 1. When I say it's order 1, what I mean is it's a number. It doesn't have to be 1. It could be 3. It could even be 1,000,000. Doesn't really matter what that number is. The point is it stays fixed as I take the limit n goes to infinity. So what we're going to be interested in is that this is the behavior as n goes to infinity of the lifetime. So tau here is the dwell time or lifetime of, say, the state with m greater than 0. So let's suppose that this is true. Okay, let's suppose it is true, and I'll show you. I'll derive it for you. But let's suppose it's 2. What does it imply? If this is true, then there's 2 interesting things that happen. It means that as I take the limit, n goes to infinity, tau goes to infinity. And if tau goes to infinity, that means I always stay in that region of phase space. If I always stay in that region of phase space, then that means that I have ergodicity breaking. Okay, so that's the first thing. So I have to take that limit, and then that time diverges, and it diverges really, really fast. And so that means that the system will basically be trapped into a ergodic region of phase space. And so another thing that this means is that in reality, we have, we never take the limit, n goes to infinity. So n is definitely less than infinity. It may be large. But how do I know if the phase transition's occurred? Well, I have to take a measurement. So if I take a measurement, then I have an observation time. What is the observation time of every measurement in physics? What is the maximum observation time of every measurement in physics?
Lifetime of the universe.
It's not the lifetime of the universe, no. I understand why you say that, but it's not the lifetime of the universe. It's the time it takes for you guys to finish your PhDs. Because all measurements are basically taken by graduate students in the lab, and you're going to get out of here in 5 or 6 years, hopefully, and because that's when your funding runs out and everything like this. So the lifetime of any experiment, you know, basically, unless you've got one that's funded for 40 years or something like the gravitational wave detector like LIGO, basically the lifetime of any experiment, particularly in condensed matter physics, is bounded above by 5 years or 6 years. Okay, so in reality, tau observation time is very much smaller than this tau ergodicity. And so when I write down this, let me call this tau ergodicity. Okay, and so what that means is, even as long as n is bigger than a certain number of atoms, then basically I'll always be able to observe phase transitions in the lab. Okay, so that's what happens. Okay, all right. So I'm not going to talk about replica symmetry breaking. Let's see. I've got 3 minutes left.
Is that like ferromagnets lose their magnetization after that?
Magnets lose their magnetization. It can do. That's a very complicated question. Why do magnets stop being magnetic? If they get heated up, if you have domains forming, So let's suppose I take a magnet and just cool it down, okay? It doesn't actually look like anything that you ever see in a physics textbook. It looks like something you see in a material science textbook. I've got some grain boundary over here, and the strings point up, there they point down, there they point up, there they point down, something like that. And then these grain boundaries may move around and so on. And so all sorts of material science effects are the things that determine magnetism in the real world. And then you may have disorder, so you may have pinning sites. So these things may move or not move. The thing may be thermally heated, it may be cycled, and so these things are moving around and gradually erasing the magnetization. So there are all sorts of mechanisms where magnetization can decay. So I think I think I'm going to stop here. Next lecture, I'm going to start off by talking about the kinetic time equation. It tells us all of these things I've written on the board, written on the screen. It tells us one other thing that is fantastically interesting. Okay, and we'll prove it later in the class using completely different methods. But look at that equation and tell me if you can see a situation where this concept may be completely wrong. Look at that equation carefully. Okay, just to help you. Remember I told you last lecture that in statistical mechanics, we have to do lots of tricks to be able to do calculations and understand things. And it behooves us to think about physical systems in different spatial dimensions. Okay, I even told you that we think of dimension as being a continuous variable rather than a discrete variable. Look at the dimension dependence in that formula. Okay,
You mean no phase transitions, right?
okay. So somebody else said something.
You mean D cube equals to 1.
Something weird goes wrong when D is equal to 1, right? In this formula here, this divergence of the resistant time is only true because it's n to some power. If D is equal to 1, that power is 0, so it doesn't diverge. Okay, so the implication is that if D is equal to 1, tau ergodicity is less than infinity. And that is a precursor for a famous theorem that some of you know, and you mentioned it at the beginning there, and that is that, quote, in D equals 1, there are no phase transitions. Okay, that statement is in fact wrong, but it's a sort of, I'm saying it in a deliberately provocative way, like you did. It's not quite correct, and we'll talk about why it's not correct later, but not today. Okay, any questions about today's lecture?
Can you point on the hysteresis that exists in the solid liquid transition? Is hysteresis essential for phase transition?